Yeah, physics is tomorrow.
All right, so this is the review session for the final for MATSE 112. So I'm here to answer any questions you have. Remember, the final will be comprehensive. So from the first exam, second exam, third exam, all the homeworks, all of that stuff. But I published a review sheet for the final, and the final will only cover the topics on the review sheet. So if it's not on the review sheet, don't worry about it. And like the email I sent out today, the final is definitely a little bit more weighted towards concepts and not as much towards calculations. So the details of some of the calculations you don't need to know. However, the stuff like calorimetry, remember where you put 2 blocks of iron, say Fe at 397 K, and this is 200 grams. You put it together with a block of iron that's 100 grams, and this one's at 200 K. What's the final temperature? You know, so this type of thing is fair game. Also calorimetry questions where, say you take water, and this is 400 grams of water at 30 degrees Celsius, and you drop in a block that's 90 degrees C, and it's made out of, say, 20 grams of aluminum. What's the final? Stuff like that. All the electrochemistry stuff that we just did in terms of cell potentials, E0. E0 cell. What other types of calculations do we do?
Delta G.
Of course, yeah. Delta G 0, delta H 0, delta S 0, delta G reaction. Remember, these two are different. So these are the standard free energies for your various processes. Delta G reaction is delta G 0 plus RT ln cubed. I think it's positive. So remember, two different delta G. Same with E0 or E cell. An E0 cell, remember E cell is E0 cell minus RT NF ln Q. Hopefully you know how to get between these two. We just had that on the third exam. Other types of calculations, I'm trying to think. Go ahead.
So there is no calculation about dipole moment.
Well, there was a calculation about dipole moment on your first exam, right? So, I mean, I'm not going to tell you what's on the final, but that's a pretty easy calculation to do. So does everyone remember what a dipole moment is?
Charge times distance.
Dipole moment equals charge times distance. So what's a dipole?
Two charges in with a distance.
That's not necessary. It doesn't have to be two charges, but some sort of imbalance of charge, right? So we have your, delta minus, delta plus here. So it's an imbalance of charge. So this is a dipole. What's the difference between a dipole and a dipole moment?
Temporary.
Well, a dipole is just the thing, right? You draw a picture of a dipole. The dipole moment is quantified number of this charge time distance. So if you know what the charge is, or the partial charges are, and you know the distance, then you can compute the dipole moment. So a dipole moment's a number, and a dipole is just a thing, right? So it's just this picture. What about van der Waals forces? So if you had a choice between methane and acetic acid, hopefully those pictures pop into your head. What's methane? CH4. What's acetic acid? Like this? Which one is more polar?
The acetic acid.
Acetic acid, right? Is methane polar at all? No. So which one has higher van der Waals forces? The one that's more polar, right? So you have dipole forces or dipole-dipole forces with acetic acid, and you just have dispersion forces or dispersion forces for methane. So which one has a higher boiling point? Acetic acid, right? Higher van der Waals forces. So don't forget the easy stuff. Remember all the easy stuff we did over the first month or month and a half on the first exam. You know, which molecules are symmetric, which molecules are polar, which has higher van der Waals forces, all that stuff. Those are really important concepts. Remember, the first exam was mostly conceptual, and so I want you to remember that stuff because that will really help you as you go on learning about different types of materials when you're done with this class. So don't forget the easy stuff that we started with. Which one has higher vapor pressure? So if I asked you, does methane have a higher vapor pressure or acetic acid? Higher vapor pressure. Higher vapor pressure means what? More volatile, right? So which molecule is more volatile? Methane, right? What if I put oxygen in there too? Which one would you guess is more volatile? Oxygen or methane? Oxygen, right? Smaller molecule, probably, even though, I mean, it's a little bit of a toss-up, right? Here's oxygen, here's methane. Oxygen might not be smaller at all. But it's, you know, it's tricky to know between these two, but once you start to introduce dipoles, then you really, it's a lot easier to get. But our spidey sense tells us that, liquid oxygen, you know, that's not so common, but liquid methane is maybe a little bit more common, right? Liquefied natural gas, and so maybe I would say that this one has a lower vapor pressure. So make sure you, when I use terms of vapor pressure or boiling point or freezing point, make sure you know physically what those things are and you can sort out what molecules are doing what. So definitely think about the concepts and the easy concepts. I mean, you know, the final, since I make it comprehensive, I want you to know the big themes of the class. You don't necessarily have to know every single little thing, but make sure you know the big stuff for sure.
Now, acetic acid would have been more polarizable in that case compared to methane, correct?
Well, I mean, it's hard to compare. So if you take methane and then you take acetic acid, you know, I guess acetic acid would be more polarizable. What does polarizable mean? When you bring a dipole close to this thing, so you bring some sort of dipole close to the molecule, how do the electrons move? So if you bring a dipole close to methane, you know, it will have a certain polarizability because you're moving all these electrons away from this dipole, right? So this negative part of the dipole comes close to methane, it's going to push electron density this way, right? Because negative repels negative. And so in this case, since you have these lone pairs on oxygen, here's some lone pairs right here as well. You know, in this case, acetic acid is probably more polarizable. It's bigger, right? There's more electrons to push around. Or, in this case, the electrons are going to be pulled towards the positive charge, right? So electrons are attracted to the positive charge. So since acetic acid is bigger, that's probably more polarizable. How fast, go ahead.
No, go ahead.
How fast do these dipoles exist? So if I say, okay, you polarize methane like this, how fast does that dipole last?
How fast is it moving?
How fast does it move, yeah, or how long does it last?
Okay, about 10 to the 10th or 10 to the
Exactly. So these dipoles oscillate oscillation frequency about 10 to the 10th to 10 to the 15th. What's the units of frequency? Hertz, right? Which means as soon as you polarize methane, in 10 to the minus 15 seconds, it's moving back, right? So these instantaneous dipoles are very, very fast. So, is there a permanent dipole in acetic acid?
No.
Yes, there is, right? There's a permanent dipole in acetic acid, and so this dipole is going to be there no matter what. But in methane, is there a permanent dipole? No. And so the oscillation frequency of the dipoles in methane are going to be very, very low, 10 to the 10 or 10 to the 15. And so this induced dipole induced dipole forces, they have a very fast oscillation frequency, or they don't last very long. And they're weaker than dipole-dipole forces, right? And so you want to have some idea of how long these induced dipoles last, or their oscillation frequency. So 1 over frequency is time, right? So that's 10 to the minus 10, 10 to the minus 15 hertz. And so the difference between these instantaneous dipoles or these permanent dipoles is something that you want to have in your head. And how that affects properties, right? So I asked you lots of things about boiling point, vapor pressure, stuff like that. You want to make sure that you know, especially some of the examples we